This meeting is being recorded.
In this last section of Chapter 16, we're either introduced or reintroduced to UV spectroscopy. And let's take a look at what concepts we should recognize here. So UV vis, ultraviolet visible spectroscopy, is abbreviated as UV vis spectroscopy. And what that's saying is that we can see light or energy being absorbed in the ultraviolet or visible range of wavelengths. So we know that visible light has certain wavelengths associated with it, ultraviolet light also. And this type of light, UV or visible, generally would provide enough energy so that conjugated pi systems, like we've been talking about in this chapter, can absorb this light energy, and this light energy is then converted into potential energy. So what we see here is butadiene's ground state. So the 4 pi electrons that we see in butadiene are distributed in this fashion. So the 2 lowest energy levels each have a paired electron. One of those electrons in the highest occupied molecular orbital gets promoted to this orbital here, number 3, with addition of light. So that's what we see here, this H nu. And now we have an excited electron and that potential energy conversion that has happened. So this is again our excited state of butadiene, and we see that this is now our highest occupied molecular orbital. And this is now our LUMO up here. Whereas before we had this is our LUMO and this was our HOMO here, the highest occupied. So we can see that conversion of light energy into potential energy. So again, in general, that necessary energy to excite an electron can fall within that UV or visible region of our spectrum. So remember the relationship that E is hc over lambda. So we can see that energy and wavelength are inversely proportional. So the higher the wavelength, the lower the energy, and vice versa, right? The higher the energy, the smaller the wavelength as well. So again, we can see that pi to pi star transition when we have that light energy absorbed here. So now let's talk a little bit more about what is happening. We know that absorbance is the value that is generated based on light transmitting through a sample. And what we see here is the equation of what absorbance is. The value that's generated is actually the log base 10 of the incident light, so the light that hits our sample, divided by the amount of light that's transmitted. So this is our transmitted value down here, and this is called our incident light up here, what hits our sample. So we can see that we have at a wavelength of 217 nanometers, we have what we refer to as our lambda max, or the wavelength of maximum absorbance. And this is specific to our compound butadiene. So there's this table that I have given here that shows the transmittance values to what we see generated as an absorbance unit. So AU stands for absorbance units, and if we have 100% transmittance, that would mean that none of the light was absorbed. So we have 0 absorbance with 100% transmittance. And then you can go through and see down to 10% light is transmitted, so 90% is absorbed. If we plug in to our equation that you can see over here, the absorbance value is going to be 2 minus the base 10 log of the percent transmittance. So that would be the incident light divided by our transmittance value. So you won't need to know how to do this calculation so much as just knowing the concepts behind it. So now that we have a conjugated compound that we can take a look at here, we can actually predict or discuss the observed amount of energy that's absorbed and the lambda max values. So Our maximum, our largest wavelength of absorbance, well, I'm sorry, our wavelength of maximum absorbance for butadiene we saw was 217 nanometers. That increases, that shifts as we have more conjugated pi systems in our compound. So we can see that our lambda max for this compound here with 8 pi electrons now has a wavelength of 290 associated with it. So more conjugation causes a smaller energy gap, and that's what we're looking at here. So therefore, we know again that relationship is Hc over lambda. The lower amount of energy needed, the larger the wavelength, right? So lower energy, higher wavelength. And that's exactly what we see above. So now if we wanted to predict what value would be given for our lambda max, we can do that using this basic system here. So we have this compound, and we have this portion called the chromophore. We also have these alkyl groups that we can call oxochromes. So the Woodward-Pfizer method will show us the rules that we can use to predict our lambda max. So we start with butadiene as our base value. So we start with this, the conjugated diene, butadiene specifically, we have a base value of 217 in this example. So 217 nanometers, right? It's not really much of a calculation, it's just our observed value. So now we want to add 2 additional double bonds to our system. For each double bond, we're going to add plus 30 to our lambda max, and we can see 217 plus 60 will give us an approximate 277 lambda max, and our observed value is around 290. So again, this is an approximation, not an exact calculation. And then we could use, say, this compound here. We have our butadiene as our base value, so that 217. And then we have 3 of those oxochromic alkyl groups, right? So these 3 that are highlighted in green. We're going to add plus 5 per each of these groups. So we have 3 times 5, so 217 plus 15 gives us 232, and that estimate is dead on. So the observed matches are predicted there exactly. There are 2 other rules that we can use to predict these lambda max values. So we have here an exocyclic double bond, so that's what we see here. So we're going to add plus 5 for each of those in our compound, and then we also have those 2 oxochromic groups, those 2 so we add 2 times plus 5 for each of the alkyl groups. So we have 217 plus 15 again, and our observed is very close, around 230 nanometers. And last but not least, now we have this specific term here, this homoannular diene, where both of our double bonds are contained within one ring, and they are locked in that S-cis conformation within the ring. So because of that, being a homoannular diene, we add plus 39. And each of those oxochromic groups, those alkyl groups, so 1, 2, 3, and 4, we add 4 times 5, so plus 20, plus 39 to our base value of 217. We get a predicted value a little bit higher than our observed. So you can use this Woodward-Pfizer method to predict the various lambda max values for compounds.